Well, and welcome to the last lecture, except for reviews, in Chapter 6. This is going to be Lecture 70. The goal here is to teach you how to deal with the irreversible part of the entropy, which we have so far always assumed to be zero. Well, except when we try to solve it specifically for it. But how do we combine the entropy as an equation of state with the irreversible part? Well, the way we do that is by a concept called isentropic efficiency. So the processes that we will describe first will be isentropic, and then we will define the efficiency, and we will show you how to apply that concept, compressors and pumps. We will give you a methodology, how to do it, and then we will define the same thing for nozzles and give you the methodology on how to do it in practical problems. So let's take a look at an isentropic process itself. So we work now in a TS diagram or in an HS diagram. So in a TS diagram, like we saw before, we had the vapor dome, the critical points here, saturated liquid, saturated vapor. And let's assume that you start at an isentropic process, which means this is a vertical line in this diagram. Start at point 1, which is at the temperature T1, get to point 2 at a temperature T2, eventually to point 3 at the temperature T3. You conserve the entropy throughout that transformation 1 to 2 to 3. Bear in mind, it's not the same as adiabatic. It is both adiabatic and reversible. This is a review from last time. So all the states on this line have the same entropy. So you can find entropy S1 in a table if you know P1, T1, or any two characteristics at this point. Once you have that, you can tell you that S2 is S1 and S3 is S1. And so if you have other properties, like for example, if you know also P2 and S1, you can find all the properties of state 2. If you know X3, for example, the quality of the steam, because you're in the vapor dome now, if you know X3 and S1, you can find out where that point is completely and characterize this state of affairs completely. So that's an isentropic process. We can do the exact same thing if we look in superheated steam, or if we look at ideal gas. It's the exact same process that you walk through. So you take verticals in the TDS diagram. Now, in general, if the system is reversible and adiabatic, then these two are zero. But in system is reversible, the change in heat in reversible system is associated with a change in entropy. This is what we did as integrals in the TS diagram. We can work on that with the PDV equations. And we know that if we set the transformation to be isentropic, then that means that dH is VdP. So in other words, the VdP integral we had is exactly the same as the change in enthalpy in that is the work. All right. Now, how do we do it? When we have an ideal gas, we can use table lookup, so between 2 and 1. If you know either V2P2 or V2T2, you can look up in your tables what the value is of S2, S0 2, because that doesn't depend on pressure. So you look up for S0 2 in the table, and then you have to know P2 to make the correction for the real enthalpy for the correction term that comes from the pressure. Because remember, the real enthalpy in ideal gas is a function of both temperature and pressure. We had to get to the reduced enthalpy, which is a function of only temperature, and then make a correction for pressure. So really in a problem like this, you end up with 4 unknowns, T1, P1, and T2, P2. But that's not unusual. You need 2 to characterize one state and 2 to characterize another state. Now, if you have a transformation to characterize, if you know any 3 of these 4, you can find the 4th. Okay, so when you use tables, I'm repeating here that you should use your tables only for the S0s, and then you can solve for T. But if you have reality, you have to add corrections for pressure. Now, in the case of air, there is a trick. A trick to simplify the lookup in the lookup tables, which I don't particularly like, but it works. Instead of using the entropies, the normalized entropies, you can use something that's a relative pressure. So a relative pressure, well, let's solve the equations for the entropy change in the case that you have the temperature dependence here. So this was this logarithmic equation that we had here. Let's solve that equation for 0. So you took S2 minus S1 on the other side. You take this log, you make that log turn into an exponential, and you end up with this equation. Yeah, P2 then becomes P1, exponential of the change of these normalized entropies, function of only temperature divided by the ideal gas constant. Well, you can pick one of these to be arbitrary. So let's take this here, the function exponential of S naught of t over r, exponential S naught of t over r, to be a, quote, reference pressure, a relative pressure. Bear in mind, this relative pressure is not a pressure, in spite of its name. It really is a normalized entropy, is what it really is, divided by the ideal gas constant and times an exponential. So this contains this term. Relative pressure contains nothing else but the entropy at normalized over pressure. If you have this as a definition, and you have that as an equation to look for your change in pressure, then you can work out the algebra. P2 over P1 is this first exponential of S naught of T2 over I, which is PR2, and then exponential of S naught over T1 over I, which is here, which is PR1. So the ratio of the pressures is the ratio of these relative pressures. It's not a pressure. It applies only to an ideal gas as air. It applies only for isentropic transformations, so you still have to make the corrections for irreversibilities. It simplifies a little bit the looking up of entropy in the tables, and it's completely redundant as far as information goes with looking up S naught of t. But it's commonly used. And one can do exactly the same thing with the relative volume. So this is the relative pressure, definition of relative pressure. You can define yourself a relative volume in the same way and come up with the same set of equations. And this too is tabulated in 22E, just like this one is tabulated in A22 or A22E. All right. So let me now quickly review everything we learned about ideal gases in the case, the simplified case, where Cp and Cv are constant with temperature. Of course, they are constant with pressure. Internal energy is Cv times difference in temperature. Enthalpy is Cp times temperature. Difference in enthalpy is Cp times difference in temperature. Difference in entropies is Cv ln T2 over T1. If you were to use a table, this is where you would have S naught of T2 minus S naught of T1. But in the case where the Cp and the Cv are not temperature dependent, this S naught ratio becomes just Cv ln T2 over T1. And then you have to correct for specific volume. The same if you work with pressure. It's the Cp ln T2 over T1 minus the R corrected for the change in pressure. So depending on your problem, if you're given specific volumes you're going to correct for, then you have to use Cv here. If you're given pressures that you're going to have to correct for, then you have to use Cp here. Of course, you always know your relations between Cp and Cv. That's just a reminder that I'm adding here. Let's apply this now to an isentropic process in an ideal gas between 2 and 1. We take the exact formula as we had before. So 0 has to be Cp ln T2 over T1, and then the correction for pressure, minus I ln P2 over P1. Or you can do the same with Cv T2 T1 and V2 over V1. You have 4 unknowns like we had before, and you had the ratio, Cp over Cv is K. Well, solve this equation, substitute, and you have T2 over T1 is P2 over T1, K over K minus 1. You have these things here, and you actually can get all your equations in here. So using entropy for an ideal gas is just as simple as it is to use enthalpy, but never forget the correction transfer pressures. Okay, so next we have to deal with the problem of irreversible heat. And this is how we do that. So this is the real system. It goes from 1 to 2 in a TS diagram or an HS diagram. But we are going to first suppose that the transformation is isentropic. So we go from 1 to a fictitious point 2s. The work in this system is H1 minus H2. The change in entropy between 1 and 2 is the heat that's exchanged plus the entropy that's produced over mass. That entropy produced over mass is positive. Now, the most enthalpy change is directly work, can then only be obtained if H1 minus H2s, which has to be smaller than H2 minus H1 has to be smaller than H2 minus H. Let's say this again. H1 minus H2 has to be smaller than H1 minus H2s. So this H2s is for a fictitious transformation 2s that conserves the enthalpy from point S1. So the maximum possible amount of work is actually H1 minus H2s, but you have to correct that for the efficiency. So the real work that you get over the work that you would fictitiously get if the machine were isentropic is H1 minus H2, which is your real work, over H1 minus H2s, which is fictitious work if the machine were perfect. Now, this sounds complicated. That's why we will develop a series of recipes to tell you how exactly to do this. But let me do the same exact thing with a pump, because it's the reverse. So I'm going to increase the pressure between this state 1 and this state 2. Between this state 2. I will increase the pressure going up between 2 and 1. Now, I'm going to have to put work into that system. So the work absorbed by the system is H2 minus H1. The system, if it were adiabatic, so let's just magnify this. We're going from 1, that's what happens. This is 1 and this is 2. We're going from 1 to 2. We are really going from 1 to 2, but we don't know how to calculate the irreversible losses if we do that. So we're going to say we go from 1 to an idealized situation that is 2s. That's an isentropic transformation. You know that the work is going to be H2 minus H1, but you're going to be calculating H2s. H2s minus H1 here is smaller than H2 minus H1. In other words, the work that you calculate when you assume the transformation is isentropic is smaller than the work you're really going to be paying. So there is a price in efficiency of your pump, which is H2s minus H1, the smaller number, over H2 minus H1, the larger number, and that is going to be the isentropic efficiency of your pump. Just like in the previous view graph, you get less work out of your system because the real H2 minus H1 is smaller than the H1 minus H2s. Just in the same way, in the pump, the real work you're going to have to put in is larger than the work you would calculate if the transformation were isentropic. This is why these machines can be characterized by an internal efficiency that is an isentropic efficiency, gives you, in fact, the amount of irreversibilities that go on in the machine. So what do we do when we're looking at efficiencies of turbines and compressors? Here is the methodology, the recipe to apply the rather complicated idea that they gave in the previous few graphs. So when you evaluate the turbine actual work, you evaluate H1 at S1 at the inlet conditions. So that's your starting point for your turbine. The next step you do is you assume virtually that your turbine is idealized. So then you calculate H2S, so you find your state 2S for an isentropic transformation that doesn't exist, but you make it up. And you get H2S and T2S at the exit pressure as measured by the anisentropic process. In other words, 2S is S1, S2S is S1. Now you correct that for the actual mechanical isentropic efficiency to get your real state 2. In other words, you correct H2 minus H1 divided by H2S minus H1. That's your real efficiency. And now you can calculate the real work, because that's H2 minus H1, not H2S minus H1. So that is how you get the final result. Now, from there, of course, you can eventually work back and find out what the sigma was of your turbine, because really it's the difference between S2 that you have here, S2 minus S1 over S2S minus S1, which is 0. So that will be the rate of irreversible friction losses and whatnot in this particular turbine that give you that isentropic efficiency. Isentropic efficiency for a turbine, maybe 80 to 90%. That's the sort of numbers we're looking at. Okay, now the pumps do exactly the opposite, except now, as we saw before, you have to reverse the denominator and the numerator. The pump will take less work to work, so the H2S will be smaller than the H2, because this is work that you have to put in, and of course nature never gives you anything for nothing. You always lose no matter what you do. The third machine that we have to look at are nozzles. So it's really basically the same reasoning, only increases in entropy are allowed. So the S2 minus S1 has to be, the irreversible losses, has to be larger than 0. But we are treating it differently here because nozzles are designed to make work, nozzles are designed to increase velocity. So we have to express the isentropic efficiency in terms of velocity losses. And the principle is exactly the same. So let's take the case where we go through an isentropic expansion without doing work, just changing the velocity. We are going to get this much improvement in velocity from that nozzle, from here, because the velocity comes from the enthalpy change. So it goes from here to here. This will cost you less enthalpy than what you really, this will get you less enthalpy than what you really get, which is the equivalent isentropic transformation. And then you express this in terms of enthalpy, which you then transform into velocities. And the isentropic efficiency of a nozzle is simply the ratio of velocities, the velocity you would get if you had a real machine, well, not the velocity you would get if you had an isentropic machine, which is down there, and the velocity you will actually really get is a little bit less than what you would get if you had an isentropic transformation. So once again, we have a recipe that translates these concepts into what you have to do when you solve a problem. You take your inlet, H1 and S1, that conditions P1 and T1. You then make a fictitious property to a virtual state 2S that has the same entropy as S1. So this is by hypothesis a virtual isentropic nozzle. Now from 2S you get H2S and T2S, but you know that the velocity you will get is a little bit less than the velocity you actually get from the isentropic transformation. So you know V2, and the ratio of V2 to V2S is your efficiency. It's actually squared because enthalpy goes as velocity squared. And so that gives you the real H2. And you can do the opposite. You can, of course, get the amount of irreversible heat that was generated, so the sigma dot, by going to the concepts of entropy instead of the concept of enthalpy. So if you look in your tables what the entropies are for 2S, since you have your condition 2s completely characterized, you can find out what the irreversible losses were. So I hope that helps. And with this, we are at the end of the chapter on using entropy.